Congratulations. You've made it to Module 6. Things start getting interesting at this point. This is the point in the course where a lot of the things that you've been doing have been a little disjointed. And hopefully you've been trusting me that they'll all actually fit together in a coherent fashion. And I'm hoping that a lot of that will happen this next week. How did everybody do on assignment number 5 this last week? Any experiences, moments of sheer terror or joy that you'd like to share with the class? Frustrations? Yes?
I was just kind of weird for me, the online database for Gazebo never loaded me, so I had to manually download it all.
Really? Did you have anybody look at it?
Computers even.
Did you have anybody look at it with you in office hours? It should. It sometimes takes a while, especially if you're not on a fat pipe.
Okay. Left it on for a really long time.
Okay. Yeah. Well, we can look at it together during office hours. It's nice to be able to have that. And what it'll do is when you pull a model down for the first time, it'll make a local cache of it.
I actually just wanted to download the entire repository.
Yeah.
Get it or whatever. So.
Right. As Gazebo has separated from ROS, become its own freestanding project, the ROS Gazebo interaction sometimes there were a few clunky things about it, and several of you discovered this during this last week. One is that Gazebo by default, if you're running regular Gazebo, wants to store models in the .gazebo models directory, and that's okay for Gazebo, but it's not actually great for us because we would like to have our models stored in version Git repositories that live within the packages, and this directory is not in the Catkin workspace, and so it is for that reason that many of you adopted the design pattern which is given in the tutorial, which I think is a good design pattern. So you can put your model here, but then you're going to have to manually remember to put it there and change things when you update your model. One thing that I've seen some people do is they do a symbolic link from here to the package, and that's okay, but it still is a little clunky. I don't think there's a perfect solution. The one that I like most is in the source directory. This is the project that you did last week. I've got worlds and erdefs here, and so the worlds I can specify directly in my launch file. I can specify this world file in my launch file explicitly, and then I can also specify this erdef in the launch file. So in my Gazebo launch file, and I think most people are doing this, get around that by so in my example launch file, I launched the empty worlds.launch from Gazebo ROS, and then I explicitly passed in the name of my world file by finding my package and appending the subdirectory worlds in the name of the file. Set this to the argument world name. There's a typo that somebody pointed out to me. I called in the website, I called that a parameter. It's not a parameter, it's an argument. So this then finds its way into my version Git repository. Similarly, setting a robot description goes to the version repository, and if you use spawn robot rather than building your model directly into, you could build your model directly into the world, or you can use spawn robot, spawn erdef. It's the package Gazebo ROS. Node type is spawn model, and you can give it a specification of your robot description. So it says the parameter is robot description, and the name of the model is as you emit my robot, and you can also give it additional parameters such as where to spawn the model. And some of you discovered that for Gazebo there's an argument that you can pass in which is paused, which pauses the physics, which can be useful because, for example, if you made your Zacro file, like I did, with the center of mass above the axle in the middle of the body of the robot, then when you run Gazebo, by the time it comes up, the robot's already fallen down. If you pause the physics initially, then you can see that it takes about a half second for the robot to fall down, and you can actually watch that little event. So you can run the physics. So this design pattern of specifying these things in the launch file specifically arises so that all the files can reside in the version Git repository of your package. So this week, a lot of stuff comes together, and I worked hard over the weekend and the last couple of days to make a new plugin to make this complete. My goal was for you to be able to simulate the robot in Gazebo indistinguishably from the actual robot. And the thing that your model didn't have was a controller. It fell down, and that's okay. So I made a Gazebo plugin. I meant to do this last year, but I didn't have enough time. And so this weekend, in the last day or two, I made a Gazebo plugin for you. And I need to update some of the graphics on this tutorial. I didn't quite get, so I'm going to make some updates on the graphics. What I want you to read this week is mostly about Gazebo messages and Gazebo plugins, Gazebo ROS. And plugin lib, I need to delete that. We're not going to actually do that. Hang on a second. Let me just edit that while I'm here. ROS plugin lib. That's something different. We're working on Gazebo plugins. So there's a way to make ROS packages that run nodes, and you can plug in other executables into them. It's a more advanced topic that we're not going to cover. There. So these are the things that I want you to look at, particularly the Gazebo ROS package documentation, messages, plugins, and Gazebo ROS. And I'd like you to do these tutorials. This continues on the version 2.2. That's a typo also. I'm going to clean this up. 2.2. I think we're at version 7 of Gazebo. So in the tutorials that I've asked you to do, and I've named them here specifically, I want you to do the tutorial called Gazebo Plugins ROS, ROS Control, ROS Communication with Gazebo, and ROS Plugins, and Advanced ROS Integration. And in these examples, what they'll do is you're going to download a package, and the package is going to be called Gazebo ROS demos. So you're going to pull this package down into your workspace and build it. And it's got 3 subdirectories: R about Gazebo, R about description, and R about control. And it has an RDEF file for a simple 3-link robot arm. You can just see it there: 1 link 1, link 2, link 3. And they give the example of the arm has a plug-in at the tip of the 3rd link with a camera on it, and has a plug-in which simulates a laser scanner as well. And so I want you to play around with those tutorials. And what you'll see in the tutorials, especially if you add some stuff to the world, that in Gazebo you can set the visualize parameter for the plugin to be true, and Gazebo will give you a visual representation of the laser scan. And then in the tutorial, you'll pop up RViz and you'll add a laser scan marker display, and you'll subscribe to the topic rbot/laser/scan, and it will display the laser scan in real time. And as you move the robot around, which you can do with some sliders, you see the laser scan moving around. You see this image from the camera on the end of the robot moving around. And so these are pretty detailed tutorials. I'm not going to go through them in detail today, because what I want to spend time on is what I want you to actually do. But do the tutorials. And if you have questions, ask me or the TAs. And there are some notes here about the tutorials. If in Gazebo, if you want to see this laser scan, you need to set the visualize true marker in the plugin. So these are links. ROS control is a set of packages that we're not going to use in the regular assignments, but it's an abstraction layer so that if your hardware uses the ROS control abstraction layer, then it's relatively easy to make a simulated robot that has the same interface. And so if you write a controller out in the ROS world, then you can connect that controller equally easily to the real robot or the simulated robot in Gazebo. And so ROS control is a kind of a little bit needlessly complicated, in my opinion, abstraction layer, hardware abstraction layer. And ROS control is used in these examples, and it's widely used, so I think it is worthwhile getting to go. And this is the idea of ROS control, that if you have hardware that has a certain predefined abstraction on how you interface to the hardware for data about the joints getting back to the real world and commands going to the actuators, then this same interface can be present in the Gazebo plugin. And so the rest of the stuff you're testing can interact. You can operate with simulations, and you can operate with reality quite easily. Why might you want to operate with a simulation? Well, simulations are the only way where we can have our robot system interact with a world where we know the ground truth, because a simulation knows exactly where everything is. There's no ambiguity. And so in actual experimentation, if we want to know for example, the tracking error between where the robot is driving and its reference trajectory, unless we have some kind of an external way to measure that, then we may not know the ground truth of how well the robot is tracking. So simulation can be extremely useful in benchmarking, and also extremely useful for developing, because you can crash robots and they can fall out of the sky in simulation and nothing bad happens. And when you crash real robots and they fall out of the sky, then sometimes you're down for a few weeks while you're rebuilding your robot. So this gives a pretty detailed example of the RRBot and robot state controllers. We're not going to be using these in this assignment, but I do think that it's worthwhile to learn them. And not just because one of my former PhD students developed this package, but his name is Jonathan Boren. He's the original ROS whisperer that I told you about. So once you do these tutorials, ROS communications with Gazebo. This tells you about how Gazebo communicates with the ROS world, and ROS plugins, very important. So you're going to be doing some plugins, and this gives a very simple example of a plugin. And in advanced ROS integration, dynamic reconfigure is nice. What dynamic reconfigure is oftentimes you have a ROS node and you would like to tune some parameters. So for example, you've got a camera and you want to be able to select the frame rate, the field of view, and a bunch of other parameters that control how the camera operates. One way to do that is to set a bunch of parameters and to kill your ROS node and then change the parameters and relaunch it. If you want to fiddle with things, dynamic reconfigure is a thing where you can define a service for your C++ node or Python node, and once you define the service, which has a bunch of parameters in it, then dynamic reconfigure will automatically create a GUI for those sets of parameters, and it will connect to your ROS node with a service request, and every time you slide one of these sliders, it'll send a new update for the entire set of parameters. And so it's an easy way to make a little dashboard where you can adjust things interactively in your nodes. And advanced ROS integration. So, and I've made a couple of notes here where if you get this particular error, then you didn't install these packages that are specified. So those are the tutorials. They'll take you several hours for sure, but it's time well spent. If you do the tutorials very carefully, then this assignment is easy. If you don't do the tutorials, this assignment will take you a long time, and you will, as my wife says, be wailing and gnashing your teeth. So do the tutorials. So here's what I want you to do this week. You pushed a package called Edu My Robot Gazebo Ross this week, and we're going to expand upon that. I've provided for you a plugin which is called Edumint Balance Ross Gazebo Plugin. And if you browse to git.lcsr.jhu.edu, here it is, Edumint Balance Ross Gazebo Plugin. You can clone it. You can clone it right now from this URL. It's a public repository. And the files in the repository, it's got obviously a CMake-Wix readme.markdown, which I haven't really, it's not very interesting plugin for balancing driving. And it's got a source and include directory. This is probably not a bad example. This is just a utility program. This is the actual plugin that I wrote, and I modeled this plugin on what's called, it's a standard ROS program called differential drive. So Gazebo ROS diff drive. This plugin is a plugin that you can add to a simulated differential drive robot, a robot that has two wheels or two treads, and it will subscribe to a twist message, and it will command the wheels of the robot, and that allows you to drive the robot around in Gazebo. What this plugin does is, I'll get to the important part is, this is all mumbo jumbo about loading physics and reading parameters from your launch file. So it loads from your launch file the command topic name, which by default is command velocity, and the state topic name. It's going to be, you're going to want to make this edumip command and edumip state. In your launch, in your SDA file or your Zacro file, you'll specify the name of the base frame for the edumip, wheel separation, wheel diameter, and the name of the left joint and the name of the right joint. And so wheel separation, right, and so this is a ROS node that's running inside Gazebo, and it's going to subscribe to a twist message, and it just stores that in a local variable. And update child is a long function. When a plugin registers itself with Gazebo, Gazebo is running a simulation, and it's doing time steps, and it's doing Euler integration on the physics. Euler integration is that position at the next time is equal to position at the previous time plus velocity times time. And then detect collisions. If there are collisions, figure out what the forces are, resolve what the forces are through all the robot models, and then update the position, velocity, and velocity based upon those accelerations and time step. And time steps are typically on the order of a millisecond or so of simulated time. They can be more, they can be less. And when you make a plugin, at the bottom of the plugin with this class, it makes this call right here, GZ register model plugin, and when it registers itself with Gazebo, every time there's a time step, Gazebo is going to call your code, and it's going to call the update child method of the thing that you registered. So every time time steps in Gazebo, this code gets called. And this is a little mumbo jumbo. The important thing here is that this thing is probably going to be called at like a kilohertz, and we don't actually need to run our controller at a kilohertz. And so I ran this controller with a argument of 100 cycles per second, so it runs every 10 milliseconds in simulation. And what the controller does is every 10 milliseconds of simulated time, it makes calls to Gazebo to get the world position and the world position and the world orientation of the edgemip base. So, and then it gets roll, pitch, and yaw from those things, and then it computes velocities, roll, pitch, yaw velocities by differentiating the current roll and pitch from the roll and pitch and yaw last time and divided by the number of seconds since last update, and so on and so forth. It makes a call to Gazebo to get the angles of the angular position and the angular velocity of the left and right joints on the robot. Those are the wheel joints. And then it creates a state vector. The state vector for this controller is the first two elements are positions. The first element, theta 0, is the average angular wheel position. So take the two wheel angles, which are absolute radians, and add them and divide by 2. So that's the average advance rotation. The second, the velocity, the corresponding wheel velocity is in the third element of this array, so first and third. The second element is the pitch of the robot body from vertical, with tilting forward being positive. And then the fourth element, element 3, is the pitch velocity, and everything's in radians. So that's the state of the robot that it abstracts by making calls to Gazebo to find the joint angles and the position and orientation of the body. These are feedback gains for a simple feedback controller that that balances the robot. So this is the feedback for wheel angle in radians. This is the feedback gain for body tilt in angle. This is the feedback for wheel velocity and body velocity in radians. And this computes the reference position and velocity so your joystick sends twist commands to this thing, and it's going to update its body and wheel references based upon that. And then it computes the feedback torque command by computing the errors. The state error is the state minus the state reference. And then the feedback is going to be the feedback gains times the error for each thing, all summed up, so plus equals. And so balanced feedback torque is the command to the wheels for balancing. And to that, we're going to add a little bit we're going to run a yaw controller, which does a PD controller in yaw. So there's a yaw reference and a yaw reference velocity. And we do the same thing. We compute the yaw error and compute some feedback gain. And then we'll saturate the feedback torque so none of these things get too large. And then we're going to output an edgemip state message, just like the real robot does, and publish it. And last but not least, we're going to command this force. We're going to tell Gazebo to set the force in the two joints with these two feedback torques. And notice that the feedback torque for the left and right wheel are the balanced feedback torque plus or minus the yaw feedback torque, so that the yaw feedback torque acts as a moment on the robot. And this call here is actually made outside of the control loop. This control loop only gets called every 10 milliseconds of simulated time, whereas this place out here gets called every time Gazebo updates. So every time Gazebo updates, it asserts these forces, but the commanded forces, torques, only get updated every 10 milliseconds of simulated time. So this is just a little walkthrough on what a Gazebo plugin looks like for a controller. And I whipped this together this weekend, and it's not very elegant. I would have liked to have shown you some more elegant code, but I was mostly interested in getting it done before today, so you could use it. And the controller is not tuned very well, so if you want to fiddle with the feedback gains and tune the controller, or come up with a better controller with some lead and lag compensation, then that'd be great. So how do you use this plugin? So what I want you to do is in your assignment, I want you to pull down a copy of this plugin into your source directory and make it with cat can make. Just to avoid any silliness, you may want to rebuild your ROS package profile. So this plugin, it balances the robot, keeps it from falling down. It subscribes to a twist message. It publishes EduMIP state messages. And you need to provide some information. This is what the plugin looks like in my launch file. In the Zacro file for my robot, I have it down at the bottom. And so this gazebo XML directive means that this is something that RViz is not going to understand, but it's going to be passed through to gazebo. So the plugin is EduMIP Balance ROS Gazebo plugin. And by convention, plugins have a certain name convention. They're the name of the plugin preceded by lib and followed by .so. So that's the runtime link library for the plugin. Debug level of 3 means that it's not very verbose. The controller will run at the update rate you specify. We need to specify the name of the frame that it's going to be, this controller is going to be acting on, the name of the link. So EduMIP body is the name of the link. That lines up with the name of the EduMIP body in the URDEF file. You need to name the two joints, joint left and joint right, specify the wheel separation, and specify the name of the topics that it's going to receive command and publish states on here. And so that's the first thing you want to do, and then you can test it out. I'm asking you to also add some additional things to your robot, but let's get to that in a minute. I'm asking you to create a new launch file that runs a joy node and a joy twist node, and so I'm asking you to, and let me show you that running. So I'll ask you to create a launch file called EduMIP myrobotjoy.launch, which runs a joy node and a joy twist node from previous assignment. Helps if you put in a joystick. Works better that way. And then we're going to run your gazebo file, and which we looked at earlier. And the thing that's changed is you will have edited your Zacro file. So it's the same Zacro file that I showed you last week. I've just added some things. And the important one is down here at the bottom is this plugin. And make sure that your wheels have friction on them. If your wheels don't have friction dialed in, if you set the friction to 0, then the wheels will spin, but the robot won't go anywhere. And when you do that, the gods smile. Gazebo doesn't crash too much. All right, Gazebo just crashed. There we go. So the plugin comes up, and if Gazebo comes up properly, you can see the plugin prints out some newsy information about what it found as parameters, so you can make sure that it's reading things properly. And in my launch file, I specified the physics to be paused, and I spawned the robot 1 meter above the ground, which you can do. And when I unpause the physics, it's going to fall down. And we're getting a little ahead of ourselves because we've already got a laser scanner. That's a later part of the assignment. And hard to see with that scanner on, so I'm going to turn it off. We'll look at the Zacro file. And bring down Gazebo. And in the RDEF, entering up my robot.zacro, visible. Visualize, any change, visualize to false. We'll get to this in a minute. Relaunch Gazebo. Gazebo ran twice in a row. Marvelous. So physics is paused, time is 0. We'll unpause physics, and you can see time is advancing at about 0.94 of real time. So here's our little robot. What's going on here in terms of topics? There's some camera stuff going on we haven't gotten to, but the main thing that you'll normally see at this point is you'll see that it's got edgemip command right here and edgemip state. You won't see this camera stuff just yet until you add additional things. And there's a joy topic. And if I take my joystick and I push it forward, the robot starts driving. So we're driving this thing in the same way that we can drive the actual physical robot. You can see the controller is a little underdamped. I didn't do a great job tuning the controller. Just got it so it didn't fall down all the time. So this feedback controller is applying torque to the wheels, and it's really doing balancing. In the real world, it's a little bit harder because you have to use real sensors, which are cruddy, and in this case, it's got perfect physics information from Gazebo. And if we look at our QT graph, you can see that what we have is joy node publishing joy message, joy twist node publishing edgemip command, and it's going to Gazebo. And nothing's subscribed to the Gazebo, so nothing's coming out yet. But if I do background, if I do ROS topic, echo, edgemip, edgemip state. There's our old friend, the edgemip state message streaming up at 10 hertz, and you can see the actual state of the vehicle. And when I drive the robot around, the state message is all going to change. And if I go back to our QT graph and I refresh, then you can see ROS topic echo is listening here, and so Gazebo is publishing edgemip state in the edgemip namespace, and ROS topic echo is echoing it. So you can interact with this, you can drive the robot around in simulation just like you can drive the real thing. So in addition to adding the balance plugin, in the RBot example, they show you how to add a simulated camera to your robot. And this is code that I used for the camera plugin. And so the sensor type is a camera. I added a link to the top of my robot called the camera link. And if we zoom in here, that little yellow one, this is the camera link, that one right there. This little pip that's sticking up here is a laser scanner link that we'll get to in a minute. So this first yellow one is the camera link. And so I added that to the top of my robot, and I connected it with a fixed joint to my robot. And then I specified a camera that had was publishing 30 frames a second, 800 by 800 pixels. This is the format of the image. It could image things between 2 centimeters away and 300 meters. It's got not a whole lot of noise in the pixels, and the plugin name is Camera Controller, and the Live Gazebo ROS Camera.so is the name of the executable. And the namespace is Edumip. The camera is always on, and these are some additional camera parameters. This is the topic for camera info, and so if we do ROS topic list, we can see the camera is publishing all of these topics. And so RQT Image View is a little Python program that you can use to view images. We just do RQT Image View. It'll pop up a screen, and it'll let us select from different versions of the cameras. Normally publish several streams, uncompressed and compressed, sometimes color and black and white, Theora images, and so these are the different images: raw, compressed, and when I drag my robot around, lo and behold, the image moves because the camera's on the robot, and you can take a look around your world. So RQT Image View. And and then I've asked you to create a launch file that will launch from I've asked you to add, in order to make this package standalone, we want to use 2 C++ files that you wrote previously, and we're going to expand upon one. What I've asked you to do is to copy those C++ files into this package, so that this package stands alone, and we can grade your assignment without pulling in multiple packages. So I've asked you to take your previously written Edumip robot state publisher. This is the one that published joint states and a TF frame. And your JoyTwist node, this is from assignments 4 and 3 respectively, and move them into the source directory of your project. So there'll be in the source directory. So here are those two nodes. And then I've asked you to then add these executables to your project so you can run them as part of this project. And I've asked you to specify a different name, so Edumip My Robot State Publisher Homework 6 and JoyTwist Node Homework 6, so you don't have a name clash with an existing package by those names. And so you don't have to change the name of the source file. In your cmakelist.txt, the source files are the same names as you had before, but you're naming the executables differently, and you can do that with this syntax. Life is easier if you don't have multiple packages with executables that have identical names, because there's the potential for name clashes. And last but not least, I've asked you to create an RViz initialization file and an RViz launch file to launch RViz. And the way you'll create the RViz initialization file is the first time is you'll say ROS run RViz and RViz will come up blank, and so you want to add a robot model, bingo, and the robot model isn't going to do anything yet because we haven't we're not running the robot state publishers, so we're not ready to do that yet. Yeah, so, and I've asked you to executable. Create an Arvis. Yeah, so create a launch file called edumip myrobot.arvis.launch, and it should load the robot description. It should launch your robot state publisher homework 6, and then it should launch a robot state publisher node. So my version of that looks like this. So you should have, in the end, you should have 3 launch files. Not that one. You should have 1 launch file to launch RViz, and it specifies that it should launch RViz with a initialization file in the RViz subdirectory of your project, and it should launch your C++ node, the edumip myrobot state publisher homework 6 version, and then it should launch the regular robot state publisher. When it does that, then we launch this launch file. When it comes up, because the joint state publisher and robot state publisher are running, when we add markers to this, then the robot will actually appear, and so we can drive around. And the markers that we want to add to this at this point in the game are, you can add an image display, and the image display is shown down here in the lower left. So there's the image display, and so so this is the image marker that we're displaying. So you do that with the add an image, and you give it the name of the topic that you want it to display, and some other things, and that will subscribe to that topic, and it will show you the image. And then, so you should have 3 launch files and run them in this order. One launches the joy node and joy twist node. One launches Gazebo with your rogue loaded and spawns a robot model. And one launches RViz and your joint state publisher and your robot state publisher. And then you should be able to drive around and do this stuff, minus the odometry markers and minus the laser scan, which we haven't gotten to yet. So I want you to be able to drive around in simulation, and you can see 2 things. You can see this is what Gazebo is doing right here, and this is what RViz knows of the real world. And so Gazebo is the full simulation, and RViz is just what is known from topics. So that's what the robot actually knows, as opposed to what the simulation actually knows. Once you have that going, then I want you to experiment a little bit more with plugins. I'd like you to add a simulated laser scanner to the robot, and follow the examples in the RBot tutorial where there's a laser scanner, and drive around. And what you see in RViz, when you zoom out, when you have the laser scanner, is you don't see any of the gas station, because RViz doesn't know about the gas station, but it does know about the camera image, and it does know about the return of the laser scanner. And so you can see that laser scanner data returned, and as I move my robot around, rotate the robot around, the laser scanner is going to hit different surfaces. And as I drive forward and it tilts, it'll hit the ground, and so we'll get a ground return, that line right there. And ask you to follow the example in the RBot tutorial. And then last but not least, I'd like you to modify your robot joint state publisher C++ node. So I've asked you in your source directory to copy your previously written joy twist node. You don't have to touch that one. And this is your robot state publishing node. Mine looked like this. And remember what this node did? It created a callback function that subscribed to the edgeMIP state messages. And it published a transform, which was the transform from world to edgeMIP body based upon that information. You remember doing that? And then it published a joint state message with the wheel angle left and wheel angle right. And the robot state publisher got that and published all the TFs for you. And what I've asked you to do now here is add just a little bit of code to publish an odometry message. So an odometry message is a type odometry, and it's going to be odometry from world to edgeMIP body, and then you need to give it the pose, and the odometry message takes a transform of type pose, and this is a TF function which converts from the TF transform format to the message format, and then it publishes, and then this publishes the pose. So, how do you figure out things like odometry messages? Well, what you need to do is read the documentation. So I'll say nav messages odometry. So nav messages documentation. So these are the nav messages, and one of them is odometry. And so a nav message consists of a header, and the header has a parent frame ID in it, and then a child. So the header right here has a frame ID for the parent and a timestamp, and then the geometry message has a pose with covariance and a twist with covariance. And that's in order for you to be able to send as an odometry message the position, 6-degree freedom, and the velocity, a twist, of your robot, and I've asked you only to fill out the pose. What is the geometry message pose with covariance? Well, that consists of a pose, geometry message pose, and a 6x6 covariance matrix, which you don't have to fill out. And what is the pose? A pose consists of a 3-vector position and a quaternion orientation. And notice that this geometry message is this is a pose message. It's not a TF frame, and so it would be useful when I look at the TF namespace reference. So it turns out that in the ROS world, there are a whole bunch of different ways to represent poses and velocities. So the physics engine that Gazebo runs will have its own internal representation for poses. TF has its own representation for poses. The pose message type, which is a standard ROS message, also represent pose. They almost all represent pose as a 3-vector position and as a quaternion of some sort. But their data types for quaternions and 3-vectors will be different. So you can't necessarily just assign a transformation from TF to this pose message, which is buried in the odometry message. Happily, take a look at the TF namespace reference, and you'll see that these are all the different things that we can do in transform listeners, transform storage, message filters, and so on and so forth. There's a class for step transform and functions, and down here in the functions, there are some useful things, which are this function right here, point TF to message, will convert a TF point to a message style point, geometry message point, and pose. Here's the function that we're going to use. We're going to use TF : pose TF transform to message, and it's going to convert a TF transform to a message transform. You could do this manually, but why bother? Because there's some helper functions to do this. So going back to my sample code, we already constructed a TF message, TF : transform, and we filled that transform with the position and orientation and time of the robot, and then we published it on the TF topic so that RViz could represent the robot. And since that information is already assembled, I'm going to use the pose TF transform to message filter function to convert that TF transform to an odometry, to a geometry message pose type, which is odometry.pose.pose. And so you need to drill into the documentation to figure this out, and then publish the odometry message. And when you publish the odometry message, and somebody's listening to the odometry message, such as RViz, you can set the marker types for odometry. There we go. So get rid of the laser scan and image. Here's the odometry. So it's odometry marker display is subscribed to EduMIP odometry, and we can control how often it will actually represent one of these things. In this case, if the odometry message changes by more than 15 centimeters or 10 degrees, then it paints a new marker. And we can adjust the length of the marker, 0.05, make it smaller. And as we drive the robot around, then it'll leave a little quiver of arrows. We can set the position tolerance to 0.02, and we'll get a whole bunch of markers. And the marker type can change 0.02, that's a lot. 0.15. And there's different marker types. You can display arrows, or you can display little frames, three-dimensional frames. And sometimes that's useful for visualizing where your robot has been. It leaves a little trail, like Hansel and Gretel leaving breadcrumbs. So, in the end, what you'll see here is RQT graph. And I need to update the graphic on the website. Your joystick node is publishing a joy message. Your joy twist node homework 6 is publishing a command. Gazebo, something in Gazebo is subscribing to that, and then something in Gazebo is publishing a camera image. It's publishing an EduMIP scan, and it's publishing EduMIP state. Your robot state publisher and joint publisher that you wrote, C++ node, is subscribing to the state, and it's publishing an odometry message. It's also publishing a TF of the base frame and the joint states from that you did previously, and you're using the predefined robot state publisher node to publish the rest of the TF frames for the robot. So that's the system, and I'm going to update the graphic here on the web page, because the graphics that were on there were for how we did it last year, which was not nearly as elegant. Questions? So simulation. Many of you chose to, like I demoed in class last time, you chose to put the center of the inertia of the mass of the robot body below the axle of the wheel so that the robot would actually stand up. In order for this plug-in to work, it needs to have the inertia where it expects it. So you should move the inertia back up to the middle of the robot body. I haven't tried, I'm not exactly sure what it'll do, but I'm pretty sure it'll fall over pretty badly. So the inertia's in the wrong place or the mass is not correct. I wrote mine expecting the mass of the robot to be 240 grams, of which 180 are actually in the body, using the sort of standard formula for mass moment of inertia. If you're within a factor of 2, it'll probably work just fine. If you're more than a factor of 2 out, it might fall over. So that's the goal this week, to get good experience using Gazebo. It's been my experience that many sort of amateur level ROS users never really learn how to do Gazebo, never really learn how to do plugins, and it really holds them back. That's one of the differences between being sort of a Stack Exchange code weenie, where you can sort of cut and paste code from Stack Exchange, and maybe it works, maybe it doesn't, but you're not sure why. But actually being able to use ROS as a tool to be able to write your own plugins when you need them, to be able to use sophisticated plugins to do simulations. And notice also that none of these nodes that you wrote here have any idea that they're getting their information from Gazebo over these topics. They don't know. So, in fact, one of the last things I asked you to do is to, and remember, when you add new marker types to this thing, to RViz, you can save the config as, and then you can save it to your RViz subdirectory in your Catkin workspace, and this is the name of the package. And so I saved the final version to edgymip gazebo RViz homework 6.RViz. So that's what I asked you to name your RViz initialization file, so you don't have to load up the markers each time. So I'm going to kill this, and is that saving? Okay. And I'm going to bring everything down. Kill Gazebo. So there's a reason that I have my robot sitting here. So my robot is here, and it's on the network, and I'm going to start killing all my nodes to bring down ROS core, and I'm going to run this program, which this launch file, edgymip my robot joy launch, and I've asked you that should launch a joy node and your joy twist node, and ROS topic list. So we've got joy and edgymip command, and down here on the robot we will run edgymip balance ROS, and it now publishes edgymip state, subscribes to edgymip command, and RQT graph looks like this. We've seen this before. And now I'm going to run the, not the Gazebo launch file, but the RViz launch file. Yeah. So this is the launch file that you create for this package, edgymip my robot Gazebo. And the RViz launch file launches RViz with your initialization file. It launches your robot joint and TF publisher and a robot state publisher. And what you can see is the exact same thing that we used for interacting with the simulation with RViz is going to work with the real robot. So now when I'm driving my real robot around, I don't get a camera image. There's no camera image, and I don't get a laser scan because there's no laser scanner. But I do get odometry markers. And so what I want you to come away from this week's module is the notion that you can have a very close correspondence between the simulated robot and the actual robot. And what I'm doing new this year, which is what I wanted to do last year but I didn't have enough time, is we've got an honest-to-God plugin which actually balances the robot. and it takes in exactly the topics that the real robot takes in, and it publishes exactly the topics that the real robot publishes. And it was a little bit more mumbo jumbo last year, and I think this is a better learning experience. Yes?
Could you show the RQT graph again?
Yep. So, so now we've got the Joy node publishing Joy, your Joy Twist node publishing Joy Twist, and we've given it a different name just so we won't have any clashes in the namespace in ROS. Edge input command is flying across the Wi-Fi to your real robot, and the real robot balancing node is really balancing. It's publishing a real edge MIP state. Your C++ node is subscribing to that, and notice that we didn't have to reconfigure the launch files. The reason that I asked you to make a separate Gazebo launch file and RViz launch file and joystick launch file is so you can launch joystick and Gazebo and just drive around Gazebo, or joystick and real robot and drive around the real robot. So we've modularized the launch files so that what you want to try to avoid is this launch file is for simulation and this launch file is for the real world. Because when you edit parameters in one, then they won't propagate together. If you do want to modularize, so you have a launch file for simulation and a launch file for the real world, make a bunch of sub-launch files, and then have an uber launch file that just includes the launch files that you want. And so your C++ program is subscribed to the real state. It's publishing real odometry, and it's publishing joint states that the real state publisher is reading and publishing the real TFs, and your program is publishing the base TF. So what I want you to see here is the close correspondence between running the robot in simulation and running the robot in reality. And that's one of the abstractions that the publish-subscribe messaging system provides for you. And so if you want to go for, if you get this done by Thursday and you're bored, then I recommend that you run you can add different sensors to your, plug-in sensors to your robot, and you could do things like, you could modify your programs so that you can drive the robot around, but if there's an object detected in front of the robot that's less than 10 centimeters away, it'll slow down and stop. You could modify your program so that you could write a node which subscribes to the ray topic, the laser scan topic, and it looks at the scan that is pointed in front of the robot, and it sends joystick commands to keep the robot 20 centimeters away from something, and then you can put two robots in the simulation. You can drive one around and the other one will follow it 20 centimeters behind using the laser scan. So none of those are required, but this is what I mean is this is where things can get interesting, because we're starting to have rich sensors and you're sophisticated about understanding topics in the ROS software ecosystem, so you can begin to think about doing sophisticated things. Questions? Okay. I knew this was going to be a long one. That's all I want to cover for today. And on Thursday, I'll have a robot of the week, and then we'll have a clinic class. So you can be working on the tutorials or the assignment if you've already done the tutorials, and I'll be available to help and answer any questions you have. Usually I know the answers, not always. Students always come up with questions that I always learn something, and I've definitely learned something again this semester with some of the questions that you've had that have been interesting. All right, any questions? Complaints? All right, see you Thursday. Have fun.